This is an Algebra 2 class, and today we're going to be looking at what a logarithm is and where we use them. Logarithms are the way that we undo exponents. It's kind of like undoing multiplication by using, for instance, division. For instance, with multiplication, we can go 2 times 6 is equal to 12, and then we can undo that multiplication by reversing it and doing 12 divided by 6 is 2. In each case, we have a different symbol to indicate that operation. So for a logarithm, it's basically a symbol that we use to undo an exponent. We can say that y equals log, this is our operation symbol or our function symbol. Base b of x means the same thing as taking b to the power of y equals x. To see what that or how that works, let's do some examples. Right now we have something written in log form. We have log base 3 of 9 equals to 2. We want to write it in exponential form. Well, in exponential form, the first thing we do is we identify the base. This is that subscript when written in log form. It's also the base. So we're going to take the base of 3, and our answer out here is our exponent. So we're going to rewrite this as 3 to the second is equal to 9. And that is a true statement. 3 to the second is 9. Let's take a look at our next example. This one, the number written as a subscript is our base. So the base is going to be 1/2. That whole base of 1/2 is going to be raised to this power of -4. And that's going to equal 16. So notice that the answer or the value of a logarithm expression is equal to an exponent. That's the exponent that we raise 1/2 to get an answer of 16. Just like we did here, 2 is the exponent that we raise the base of 3 to get 9. 3 to the power of 2 is 9. Okay, on number 3, first thing we do is always identify the base. It's the subscript. So our base of 5 and our exponent is our answer to our logarithm expression. So it's -1, and that equals 1/5. In our next group, we're going to go the other direction. We're going to take an exponential form and we're going to write it in logarithm form. So again, we're going to start by identifying the base. The base is 4. So in this case, we're going to write log base 4 written as a subscript of 64, and that equals the exponent of 3. We can look at it as being kind of a little loop here where we go back and forth. Okay, number 5, again, we want to identify our base. Our base is 5, so log subscript. The base is written as a subscript on a logarithm. So log base 5 of 1/125 is equal to the power, the exponent of -3. And again, log our base written as a subscript, 2/3 of our power here, our 4/9 is equal to the exponent of 2. So that's the way that we switch back and forth from writing from log form to exponential form to log form. Okay? So when we evaluate logs, we think backwards. Just like when we did division, we had to think about multiplication to answer those. Let's take a look at a little thought experiment here. If we want to do 24 divided by 6, our mind goes into multiplication. We would be thinking, let's see, 6 times what number is 24? And we'd think about that and we'd go, oh, that has to be 4. So we conclude that 24 divided by 6 is 4. So I had to first think about multiplication in order to do division. In the same way, when we do logarithms, we have to think exponents. So if I want to evaluate the log base 4 of 16, I have to think of it as an exponent. I have to think, here's my base of 4. 4 to what power is going to give me 16? So my thought exponent or my thought would go, oh, I know that 4 to the second is 16, so the exponent has to be 2. So I know that log base 4 of 16 must equal 2. So thinking backwards. So let's practice a few evaluating logarithms. I want to know what the value of log base 6 of 1 is. So I have to think backwards. I have to see, gosh, I have a base of 6. What power should I raise it to get 1? Well, I know that anything to the 0 power is 1. In particular, I know that 6 to the 0 power is 1. So I know that log base 6 of 1 has to equal 0. Let's do another one. We have log base 10 of 1,000. I want to find out what exponent I need because the answer to a log expression is an exponent. So I'm thinking of 10 to what power is equal to 1,000. And we know that that's 3. So I know that log base 10 of 1,000 is equal to 3. Now, answers to logarithms could be negative numbers. We're going to have a situation in number 9 where our answer, our exponent, is negative. So we want to find the value log base 1/3 of 27. And I'm going to think mentally 1/3 raised to some power has to be 27. Well, I'm going from a fraction to a whole number, so I know that I need to have this flipped upside down. So it's going to have to be a negative exponent. And I also know that 3 to the 3rd is 27. So I'm going to put those two together and I'm going to go, gosh, I bet 1/3 to the -3, which would flip this upside down, is the same as 3 to the 3rd, which is 27. So I know then that this exponent, the exponent that I raised 1/3 to get an answer of 27, has to be -3. Log base 1/3 of 27 is -3. Because 1/3 raised to the -3 power is equal to 27. Now, since exponents and logarithms are inverses of each other, that is, they undo each other, like, for instance, squares and square roots. For instance, we have the square root of x squared equals x. We can also conclude then, if I take b raised to a power of log base b of x is going to get back to x, because these operations, exponents and logarithms, are inverses, just like squares and square roots are inverses. So we have b raised to the log base b of x comes back to x. Also, log base b of b to the x equals x. Okay, a composite of inverse functions always comes back to x. Okay, let's see how this works. On this first one, I'm going to work it two ways. I'm going to work it using our inverse properties, and I'm also going to work it step by step by evaluating the logarithm so that we can see that we get the same answer. By using inverses, I see I have base 2 raised to the log base 2. These two have to be the same in order for them to be inverses of 8. Since these two have the same base, the exponent and the log undo each other, and our answer is just 8. Let's convince ourselves that that's true by doing it step by step. Let's do, by order of operations, let's do this exponent first. So if I want to find 2 to the log base 2 of 8, I'm going to do this part first. And I ask myself, 2 to what power gives me 8? That answer is 3. So this simplifies to 2 to the third, which is 8. And we get right back to where we started from here. So these are inverse properties. Okay, so using that property on number 11, we have 5 raised to the log base 5 of 25. These two are the same. So using our inverse properties, our answer is just 25. Doing it by order of operations, I start by doing the exponent. Looking at log base 5 of 25, I ask 5 to what power is 25, and that value is 2, so I'm left with 5 to the second, which is 25. You see how we get right back to where we started. Okay, so on number 12, using the properties of inverses, we have 4 raised to the log base 4 of 3x. The two bases are the same, so these undo each other, and we get just 3x. Let's do the same thing here, using our properties of inverses, where we have log base b of b to the x is just x. The base b's basically undo each other. Log base b raised to a power, reverse each other, so we get just x. So as I look at this one, I see I have log base b of a base 5 raised to the third. These are the same. These operations reverse each other, so our answer is just 3. Going step by step, mentally I can evaluate this. I can ask myself, 5 to what power gives me 5 to the third? The answer is 3. 5 to what power gives me 5 to the third? Well, it has to be 3. Number 14 here, using the same properties, I have log base 10 of a base 10 to the negative fourth. These operations undo each other. I'm left with negative 4. Because I know 10 to the negative 4 equals 10 to the negative 4. Number 15 is a little bit tricky because these bases aren't the same. So I have to get them the same base. Well, 27 I know is the same as 3 to the third, so I'm going to replace 27 with 3 to the third, and I'm going to rewrite this log base 3 of 3 to the third to the x. And now using my properties of exponents, a power to a power is multiplied. This becomes log base 3 of 3 to the 3x power. Now, our base of our logarithm and our base of our expression here are both 3's, so these two undo each other, leaving us with just 3x. Okay, using our calculator now, we can do logarithms on our calculator. Logarithms with base 10 are called a common log because our number system is base 10. And we frequently leave off the base when we write logarithms with base 10. We do that because we're basically a little bit lazy and we don't want to write it out. So when I see log of 100, I know this means log base 10 of 100. And I ask myself, 10 to what power is 100? Well, I know 10 squared is 100. So I know that the log base 10 of 100 is equal to 2. Okay. Similarly, in number 17 here, the base is not given, so it's base 10. So I'm looking for log base 10 of 1 over 1,000. And I ask myself, 10 to what power is 1 over 1,000? Well, I know I need to get it in the denominator, so I know I have a negative exponent, and I know 10 to the third is 1,000, so this value has to be negative 3, because 10 to the negative third is 1 over 10 cubed, which is 1 over 1,000. Okay. Now the other ones we're going to do on our calculator because they're not integer values. when I look at log base 10 of 28, 28 is not an even power of 10. I know 10 to the first is 10, 10 to the second is 100. So my answer here, my exponent, is going to be somewhere between 1 and 2. Well, our calculator can help us find that. Let's go to our calculator. We have our calculator screen here. The button for logarithm is on our left-hand side. It says log. This one is always the common log. It's base 10. So when we push this button, it's telling us we're doing a base 10. And if I want log of 28, I just put that in. And we want to evaluate this to the nearest hundredth. So to the nearest hundredth, this value is 1.45. And we want to do another log. We want to do log base 10 of 34,621. So let's do that one. And I get 4.54. 4.54. Okay. What this tells us is if I take 10 and raise it to the 4.54 power, I'm going to get approximately 34,621. It's not going to be exact because I rounded my answer. Okay, our next one here looks a little bit different. It has the letters ln. This is also a logarithm, but this is logarithm base e. We write it using ln because we learned that our base e is our natural base. So n is natural, so this symbol means log natural base of 275. We have a key for the natural log also on our calculator. It's right below the log base 10. Here is our natural log key, so I'm going to hit natural log 275, and I'm going to get 5.62. What that tells us is that e raised to the 5.62 power is approximately 275. Okay. Our next one is natural log, log natural of 1, and we can do that on our calculator. So we can do log natural of 1. We're going to get 0. And what that tells us is e to the 0 power is equal to 1. That's true. Any base to the 0 power is equal to 1. Okay, so that's our introduction to writing logarithms and evaluating logarithms and their inverse properties.